Okay, salam and hi again. So this video is specially dedicated to explain the example 4.2 in the textbook. Okay, so the quality of the video is not so good, but okay, but I think you can understand the video. Right, so example 4.2, the question is, okay, so the question is settling column analysis of type 1 suspension. So this is very important, type 1 suspension. Okay, so remember the settling have 4 type. Okay, so this is the first type, and then the column is 1.8 meter deep. So this is the data and this is the flow rate. Okay, the Q. Right, so let's have a look on the solution. Okay. Okay, in order for us to understand example 4.2, so this example is about settling column in type 1 suspension. So before we can understand this example, we need to understand the principle of settling. Okay, so if you refer to the figure 4.6 here in your book, okay, we are actually wanted to define the area that yang that have slash tu. Okay, this area. Okay, this area, right? So if you look here, it's actually the y-axis. The y-axis is actually the x fraction of particle. Okay, while versus settling velocity. So from the equation of to find the settling velocity, which is v naught is equals to z naught over t, you will define the settling velocity and the fraction remove. You can do like this, and then you will determine it from the graph, right? So the area above the settling velocity, okay, is actually have been fully removed. So we wanted to know the area here, right? So similar question here. Okay, so the question we're asking you about what would be the theoretical removal efficiency, meaning your x lah, your total x, okay, in a settling basin with a loading rate of 25 meter per day, right? Okay, in the question given to you, these two data, right? Time and concentration. So in order for you to find x, you need to convert this data to this table. Okay, because later we wanted to plot the x fraction, the x mass fraction versus velocity. Okay, settling velocity, like the one that in figure 4.6, right? So here, okay, how you get this value? Okay, this is actually from equation x equals to ct over c naught, right? Okay, so for example, okay, so this actually there's some mistake in the, it's either you replace this 1.8 with 2, then only you will get all this value, okay, or if you remain 1.8, the value would be more or less the same. So let's say we implement the column depth is 2, right? So for instance, how we get 0.63 here? So CT over C naught. C naught here, we know that from this table, C naught is 300, whereas CT at 60 is 189. So 189 divided by 300, we will get something around 0.63, right? Okay, next. Okay, so similar goes with all the value here for mass fraction remaining, right? So for VT, how we get the value of VT. So earlier in page 118, we know that VT is actually, okay, is, okay, here, remove here, it's the same thing. This is the one with my handwriting. So VT, okay, VT is actually Z over T. Z is distance, T is your time, so it will be in meter per minute, right? So for instance, how they get 3 here at 60. Okay, so Z naught is 2 meter, because Z naught will be your initial, your depth lah. Okay, so 2 meter over 60, because the timing is 60. Okay, so it needs the velocity would be around 3 to the power of 10 2, right? Okay, so the next example is V at 80 minutes. How we gain 2.5 is actually again Z naught over Ti. So Z naught is 2. Okay, the time is 80. So 2 over 80, it will have 2.5 10 to the power of 2. Okay, so now with this two value of x and vt, you can plot this graph. Okay, you plot first, then you will get that point, and you have the curve here. So your objective is to find the area here, not area under the curve. The area under the curve we can find from integration, like Simpson's method. You can solve it using Simpson's method. So this one is actually you want to find this area. Okay, so the next page is actually explaining you on how to solve the area here, so that you will get the total mass removal. Okay. Okay, this one is the continue from the previous previous video. Okay, so you can the step 3, you determine the V naught. This is your loading rate, so it will be 1.74. Okay, again, how you can determine X naught, number 4, is by the graph just now that you have plotted. So you determine just now your V naught is actually around 1.74, right? So it's around here 1.74. Okay, and then you extrapolate to your y-axis, and you will get your x equals to 0.54%. Okay, 0.54. Okay, now we go to the 5th one. This is the part where you are actually using the numerical method, or the one knowledge that you learned in CRE 1, but not the Simpson's rule, to solve for this value. Okay, if you look clearly here, the example, the solution is actually divide it into a rectangular. You see, you can see the rectangular. Okay, so it divides, it gives you in the middle point. Okay, if you check back again, it's quite difficult for me to explain here in the video. I just give you some key points here. Okay, so you go back again, but it's actually to solve, this is mathematics, this is to solve the area here. Okay, then once you get this value, so the total removal efficiency, this is from earlier equation, so just plus that one just now, and end up you'll get somewhere 72%. Okay, so this question can only be done when you plot it using a graph. Okay, proper graph. You sketch, you might be a very macam banyak lari lah. Okay, tak tepat. But if you can use, maybe you can try to use Excel. Okay.